just recording myself again. Okay. So basically, this is what I'm saying about. So this is the Gaussian. So the Boyle's law is just literally just the problem of the thing I'm saying. I'm gonna give you the model of it, but I don't wanna give you the wrong model. But I'm gonna give you the right model of this. You see this thing, the animation showing the relation between pressure and volume on a mass. No, this is wrong, guys. This is wrong model. I don't like it. Namely, this is wrong model, guys. This shows the mass. Today's date is 8th of December 25. The night time is 9:35 p.m. So you get the mass. The mass is being pressured down. So the volume increases and the area increases. This is wrong. This is wrong measurement. This is the wrong measurement. This is very wrong. So this one I'm saying is a piston. A piston is what? Pressing what? You got a piston. What's a tungsten? I don't know. Oh, tungsten steel. A piston pushes, but what? Weight carries. This is just the problem here. Pressure and temperature. This is not even the right amount. So the pressure is the piston thing that pushes. And let's say push and pull. Anything that push and pull affects the system weight. It doesn't have to push and pull. The piston is just the kind of homework. It's just a system reason. So I'm gonna give you that to go by because you guys are understanding this from me. So I'm not. So you got a piston. A piston is what? This is the piston. A piston is this is what I'm saying. It's like a piston. But this is the piston, it push and pull. This is what it does. It just push and pull. It's lever, so you can get two types. So this is a piston, internal combustion engine. A piston what? It's a component of reciprocating energy. Reciprocating pump. It push and pull. It's like it just does one thing and does it perfectly. It has to do it perfectly. It doesn't matter what it's a perfect system because it doesn't think about. It knows about its state. It works on the inversion. It pushes and pulls. It pulls and pushes. The volume will start. Can start with a push or pull. That's what it is. What can you put? This is like so you can get a gas compressor, but this is a gas compressor. You push gas, but the compressor has to push gas some way to get some volume. This is a hydraulic cylinder, but it's a compressor. So the thing about the piston is like it's push and pull. We get the tungsten, which I'm thinking of tungsten. I don't even know what tungsten is, but I think it's related to a piston. So let me just search it up. Tungsten. Still, tungsten cube. Tungsten is a no. This is a metal. No, something about. But basically, this is metal, but it's which is tungsten. You can push tungsten. You get the tungsten. Basically, let's go to the 1 This one. So the piston is what pushes. So the piston is like weight. So what is 1 kilo or 1 kilo? Let's do this actually. Let's use tungsten actually, because we get tungsten kilograms of tungsten. Let's just do this actually. Let's do it properly. Piston, because the tungsten is iron, so we use tungsten. Tungsten. Let me just do it because I use piston. Tungsten and with 1 kg of tungsten. That's how much is that? 1 kg of tungsten as well. Basically, this is my think about price. Just with tungsten still. 1 kg of tungsten to piston and 1 kg to piston, 1 kg piston. So you think about this thing. The phrase 1 page is basically this is a tungsten still. But look at basically how much can you buy one piston? Can you buy one? No. Basically, I'm looking at the size. Okay. So if you have, I'm saying literally, you get a calculator. Or kind of dimension of the air. So, if you have a piston that's 1 kg, 1 kilogram, you have the same thing. That basically this does one thing: push and pull, push and pull, push and pull, and push or pull, and get the weight. The weight is the piston. So the piston weight, what the piston is pushing and pulling, the tungsten. The tungsten is the iron ore, the kind of mineral you push and pull. When you go switch, you can think of the tungsten ore. You can think of it when you're being processed. You can think of it if you're gonna process an ore. I gotta make the ore here. So the tungsten is like the metal you're compressing or decompressing. So you're pushing and pulling the tungsten. Just something. That's what you think about. You don't think about space and time. Think of it as dimensions. So the shear one state of dimension. So if tungsten push and pull, there's a push and some push on them. But if the piston pushes something, so the pressure, the force of calculate piston force calculator. Because yes, so basically PCI. It would be basically this is the piston force. So the bore diameter. Basically, this is based on pipe. Basically, you see, this is the bore. That's what I'm saying. So you got a bore area, the bore cylinder, but the piston force is the same. So let's calculate this bore diameter. The diameter is 12. 12 the bore area is 12.5. Let's do 10. Let's do 15 because I love this kind of pi numbers. 15 cylinder pressure psi. Basically, you just squeeze how much you push the system. But it's kind of scary. The psi is the standard scale for pushing stuff, the piston. But the piston is just a scientific device for compression them. But when there's under pressure, what do they do? Because piston is just a measure of space and time in that system. So this is a psi scale. Pounds per square. I mean, how many pounds per? Okay, good understand is power per square inch, and just the psi is like literally I don't know these people. Pounds is 12. So let's get 6. Let's get half of. Let's get 5, 10, 10, 10, 10. We can get 5 minimum because there's no change. Because if you measure 5, that's what we get nothing in standard scale. But this one has the equivalent to the tungsten model. So this model, the boy, gotta get equivalent. So the bore diameter of a frame gives you the bore area of 17.6 0.6 meters millimeters squared square millimeters or square millimeters but you know in centimeters will be 1.767 bore area. It covers if this diameter. Basically it's the force acting on itself, but you have the ability space and time, but this is force and weight. Basically I just know the problem of the problem. Basically get the newtons, so you get 6.089 newtons or kilonewtons is what? Pound newtons. You get pound force. Basically, this one I don't really need. This one is the one that my course use. 1.3695 bore force. But the pound force is the newtons equivalent of 6.0829. So basically, this psi is a pressure dynamic. It's the dimension of the oil shear. But if you think of it this way, if you think of a teleporting, I'm gonna give it to you guys as teleporting. But you know, you got two left state, the oil shear. For example, you get two chemical state ocean, and then between one right axis. They have one left. They share two left axis. They have to share two left axis. What I mean by that, you know, you have to double the force you use twice. For example, if you have two left axis, we're talking about going left, north, east, south cube, south times south. That will be south square. This is the left axis. Northeast, south, no. Going west cube. What's the power 4? See, what's the power 4 is actually the share. What I mean is the share two left to one right axis. What this means, you know, whether the pressure or the time is different, the dimensions have a two left rotation. Because literally it's two left rotation. Two left axis. You have to take two axes of rotation. You have to change your view, like your angle, to that problem. For example, left is if you're observing gravity from another dimension, you are being pushed away, pulled away. Basically, if you're the dimension that is how can I put it? Say we have redshift, we are in dimension, we are observing redshift, we move it away, but we're pushing away. Our wave is pushing, our wave is growing. But that means we're pushing away from everything that we don't know. So it's growing, it's imploded. So we're growing in our own way. We live it. That's why we get a redshift. But you know, if I'm trying to observe this state and I'm moving away from it, I'm getting redshift. I'm getting a static wave system. But you know, that means the system is dynamically moving because I'm outside the universe, for example. That means I'm getting some state that's arbitrary. That's the measure. Can get some noise, basically. If I'm moving away from all the things, and I'm moving away from all the things that's everything and nothing, this is a state that's a still that can measure from that state, measure my own universe. Basically, I don't think about this problem, but it's a dimension I can access. Okay, let's talk about it. That's a bit harder for me as well, but you know, it's just because it's you. So I'm saying we go west cube. This just means west times west is one stable state that remembers everything and nothing of pressure and volume. Because the piston applies pressure and the weight gives volume. So the weight gives mass. Basically, the weight adds on to the dimension of XYZ, while the pressure but these pressure weights are mediums. They're not anything else but mediums. Think of it this way: they are just places that you already know of, but you can't observe because you already propagated that wavelength. For example, let me find the so this is a pressure. This is my model here, but basically shear 45 degrees psi. basically the shear half a state, the shear half a state, a quarter, the shear quarter of a state, but. See, this is wrong. This is mass and temperature. So this is mass. The mass is not really the problem. It's the temperature that's the ability. The mass is the basically. If you measure the mass, you get a temperature. If you measure the mass, you get a temperature. If you measure the temperature, you get a mass. So I'm saying in this model is not really accurate because the mass is not changing. The mass is not changing. The mass here is not growing, but this mass index actually changing. It doesn't matter. This is not going. Basically, you get volume that's 6. 6. Volume that's 3. You get 6. But this is wrong. Why? Because the pressure is increasing, but the volume is decreasing. So basically, you gotta remember this word is called. What is it called, Damn? When pressure is this is called a correlation. A correlation. And that's what you gotta know. Correlation. Because it's dimensional, basically. Dimensional work on correlation. So this is just what I'm saying. Dimensionless vectors are correlations. They're not dimensionless. They're just they have the shear inverse state that give it that dimension. They're distant. They don't exist together. They don't never exist together, and they're different systems. They want to stay different. They're distant states. So they have a correlation. So basically, this piston, if the piston pushes, if you have a weight carries some. If you have weight carries so you have 500 milligrams. So you have 500 kilograms of something, and 500 kilograms, and you have 5 on 2 axes of weight, 2 dumbbells. How do you weigh them? Those do a balance of a half and a half. But if this half is what a dimension. This half is one dimension. Basically, the shear is so this is the same thing. This weight thing, 500 kilograms. Over basically these 2 axes of weight. If a force affects a weight, basically I won't do it properly. So a piston pushes. A piston will push a dimension, but someone will push it. But this is a piston pushes something, but the pressure is wrong. So this is like a weight. This is an equilibrium of piston, but this is thing that can correlation between system. So if you get one as a weight, you get one as a piston. A piston pushes, compresses and decompresses. You just pushes and pulls, but we call it compression. Why I say push and pull is because it's a piston, but it compresses, it forces, it triples, it quadruples the force it does. And that's what's called pressure. Basically, you put your hand, you don't do anything like serious pressure like that. But if you have some kind of state, you have pressure on the state on your system. That's what will give into the pressure, and that's what the thing doesn't really matter here. So you get the pressure and the temperature. The pressure and temperature, that's what's wrong about it. It doesn't give the full picture. Because you can always change the pressure by 10% at each interval. Why 10%? So you have 1,000 kg. 1,000 kg is the same as what? 500 kg. But in pressure, like the pressure is like the force action on object is 500 kg. But that force is like when those together, something like they get a half, a quarter plus a quarter. But you get a space-time diagram. This is what you want. Space-time diagram. You get a space-time diagram of pressure. And this is what the first represents. So the more space you have, the more volume you have, the more space you have. Let's call it volume, because I don't do volume. The space of volume, let's call it volume for sure. You get something you can compute for. That's the pressure. The pressure. But this pressure is just basically you get the pressure, which is the compression of the pressure. But this is not really good enough. It doesn't tell you. In order to bring it doesn't tell you the impression. You need you don't tell you this is the problem here. This is the real problem here. The real problem is you get a volume here, but the volume is the x-axis. So the pressure is the power. Volume is the power. Sorry. So you get the axis. You get the axis of power. This is power. P for power or PSI power. The power of the system is literally just the power to the key, so the power to the volume, but the volume is a compression, so it gives noise. It's noisy. So why does it matter? Because it's noisy. So volume is not static. It's a dimension, and that dimension is noisy. And noisy can be noisy. That's what the problem. That's what really matters. So when you get pressure, when you get something that applies a force. And that force is a piston force, and it's it goes in increments. It goes from 0, 25, 1,000 kg divided by 4. I'm trying to do it. 1,000 divided by 5. No, divided by 10. Divided by 10, 100. That would be 10. So this would be 100 units. No, this would be 1,000. But 100 divided by 10 again. Divided by 5. We'll do 5. That would be 2. 1,000 divided by 10. 15. Let's do 15. Because let's do 100,000 divided by 10. Basically, divide basically 1,000 divided by 100. Because I'm thinking about basically go 100 divided by 1,000. Basically, you can usually do the model. So the number 0 to 1,000 or kg is literally just the same thing as it goes to be tens. So that'll be more easy to compute. So this is a pressure. This is a piston pressure compression. We get the we can't really measure the opposite axis of this because you have to flip the dimension. That's what it is. You have to just flip the dimension. I'm sure you guys here. You have to flip the dimension. You have to like so you have to take a picture. You have to change your coordinate system. You have to flip the whole dimension. You know what I'm saying? That's what it matters. You have to like flip it. I'm just gonna serious. I'm just gonna put it. So that's how it works. So you get the x-axis and get the y-axis. So for example, get the 1,000 kg on the x-axis, and that will be the what we call the pressure of the power pressure. Now the power pressure is because of the power piston. It's a piston, and this piston will be so you have if you're measuring x squared plus y squared equals r squared, where r is 0.5, where r is 0.5, you get 1 and 1. Which you get the full dimension of this x-axis, but this dimension has the tomographic opposite of the system. So when r radius is what, -5. -5, you get -5 squared. This will be minus 5 squared will be s squared minus y squared equals -5. Because you work on the inverse axis. So this is why I'm saying it matches to me. Basically -5. So basically back to the system. So you get the system here, but there's two. You have to flip something. You have to rotate it in two directions. You have to reorient it. So this one must you have to reorient it. So we're back to state one. So this is like so you have two axes of x, y. This is plus x plus y, and that will be 0.5. This is 0.5. This will be this axis of pressure. Pressure will be piston pressure. That will be piston. Piston. That will be piston. This will be the piston pressure, but this is the axis. We get the opposite axis, which is like there'll be the opposite one. So this is like more of noisy air. This one basically, if you imagine this is a piston, this is the power, 2 over what? This is power. X. This will be piston volume. This will be the volume that it gets. Because if you get pressure, you get noise. So this noise is what you get at measure, but it's noise that's data. It's kind of noise. Basically, if this is space here, if the volume dissipates, it doesn't go into nothing. It goes into our system, and that is what is happening in the pressure system. So in the pressure system, so you get a kind of inverse joint. Because if the pressure is void, that means the weight. So it's kind of a content switch. So you get half and half. So half plus half, basically, you get 5. This is like a 1,000 kilograms. Now you get minus 1,000 kilograms. But if you flip the dimensions, you're looking at 1,000. Basically, 1,000 kilograms. But that's shared between 500 milligrams of the weight. And that's what really happening here. So you get x squared plus y squared equals r squared, and get s squared minus y squared equals minus 0.5 minus r squared, and that will be pi r squared system. So you can complete that interval in space and time via the Deriavt framework, via buoyancy. Now, buoyancy is very important to understand because everything is buoyant. So if it's buoyant, because I think it's like water. If you don't understand what I'm saying, this is buoyancy effect. So if you drop something that can float in water, think of it. Buoyancy just affects let me try and mention it. So buoyancy, if you have a medium of water, a liquid medium, and you put some kind of a ball in some kind of bouncy ball, what's it called? So it's buoyant, that makes it start flow, but you push with a force. It will this is like a liquid water, this is like an ocean. So this is what I'm saying. If you don't understand what's happening, this is how you calculate it. So this ocean is the noise, but it's not noise, it's like because it's in the medium, and that's what this guy feels like doing. So it's in the middle. So if you drop something like some kind of missile in there, and it has some kind of beach missile, you have to sink it first. So if it takes half the time in one medium, it takes half and half the time in a more dense medium, and that will be how the system works. So if you have 0.5, you have 0.5 to the power of 1, but that will be 0.5 power of -1. So it's -1 and -1 is what it's -1 and 1. Depending on how you look at it, but get half of the half is dense. You get 0.5 to the power of I didn't do that. So get 0.5 0.5 to the power of 4, to the power of 4, and that'll be basically this 1 minute times to the power of 2, so you get 0.5 to the power of 2. So if it's 0.5 to the power of 2, this is 0.25. So basically, when something has a force, it ends 0.25. 0.25 is just say the force is what? The force is what? If the medium slows it down, has the friction of force equals mass acceleration. Net force equals 0. Net force equals 0, and energy equals mass acceleration. If the mass is what 500 kilograms, 500 kilograms of something that's buoyant like water disperses the force, and basically it's buoyant because say you join like some kind of large something that's floating like some kind of water something that goes in water and buoyant can flow some kind of, try to sink a duck. But the duck was like a rubber duck. It's a big rubber duck. You dump down a good from a height of like height 7 feet, 9 feet, 10 feet, 10 feet, 10 feet, 10 feet, 10 feet. So get 10 feet, 10 feet. Let's do it height. It's 10 feet. A rubber duck, a big rubber duck. Let's say how many grams? 500 kilograms over 10 feet. That would be 0.5 kilograms per second. But you got gravity. Gravity is just the dimension that models, that sees everything, that glues everything. It's just it has to equalize to glue. So this is just one dimension of space and time. And this means you get out 500 divided by what? Divided by 10. Wait, not 100. 10. So sorry, 500. Because 1 second. 500 divided by 10 is what? 50. 50 kg. Not 0.5. It's 50 kg. Because that's 500. You get 50 kg of force at a time. This is like a interval decision. So you get 100 kg at a time per second. But this second is not a G. So get 9 per second. This is the calculation. So gravity will be how to hold. This is because this time gravity really hard in the left more, but it doesn't stop there. Basically, the left one is like a gravity model. So I'm thinking left because left is a gravity body. They work on the axis of gravity. We got the mu ones. The mu ones is the basically it means that get the mu ones hold the left ones, and the left ones do the hold us, which is gravity. But the mu ones are half of half. So that'll be half of it. So that'll be but if you drop this on a new one, if you drop this on a new one, mu field, the quantum mu field, you get it to the power of 4. That'll be like so if the gravity is 500 degrees on Earth, 100 degrees and we drop it at divided by 10 kg, 10 seconds, 10 feet. So this will be the feet. Now the feet is just the feet, but no, this is not time. This is the feet. This is the height in feet. So 10 feet will be 0.5 feet per second. But if you get this will be 4. Basically, if this was 10 feet, this would be gravity model of what 50 kg. But this will be in a muon world of 100. So this stuff will be automatically 100 because you get 8 times 100. You get 10 times 10. Basically, it's stable. Basically, means like 10 basically has double the mass of it. So you get half basically. If this is half, 500 kg to the power divided by 10 is what 50. 50 feet. Now, 50 feet is just gravity. Now, if you get 50 feet divided by 10 again, will give you what? 100. So this will be a 5 feet. So the we take 5 feet. 5 feet for something with that a muon to something that's a electricity. It takes 5 feet for this system to get some. So you get 10 feet. So 10 feet. So you double this one. So 10 feet is just a standard model, but in this medium we just double it. So basically this half is like the half feet. So this 10 feet just 10 feet of drop. Now if you do the 10 to the power of 2, it will be 100 feet. 100 feet is 100 feet. Now 100 feet is now the state of the water. So you have to cut it by half. It's actually the ratios are half, but in this is water. Because the water slows things down because it's more dense, really packed. I don't know the nuance of it. Basically, they hold things for longer, better. They hold things forever, indefinitely, because they hold this because they hold the state already in. Basically, this is like a compression. So you see, if you compress something, you already have a medium volume, and that volume is so dense you can't compress it more. But so it slows down more. I'm saying it slows down more because it's so compressed. Because it's so much more. Whether gas or liquid doesn't matter. It slows down more. You don't pump it. You compress it. You have to decompress that space to get more space. Which is a vacuum problem. So you get 500 now divided by 10. So 500 kg divided by 100 is what? Kg is what? 5 kg. Now 5 kg is like the oil, basically, this weighs 5 kg in water. If you are in that medium, but that medium is not good enough. Basically, this medium is a polar axis. It's a polar axis. So 5 kg is just one medium of the system. So this is what, if this is liquid water, if this is like an ocean that's densely packed, you get like a solid liquid gas. So this is like this one's water. So this top one's gas, and the other one, this is water. If you drop from water, if you drop from water, the Boyle's law of the refraction will just double. So you have to try to reorientate your angle, basically the speed. That's what the refraction really matter. Because you have to travel on some kind of space. The refraction is there to slow you down, but slow you down safely. When you measure the refraction, you measure 1 over the fraction unit. This fraction is 1 over the system, but this one for you have to this 1 over is like get a measurement, but you don't get fully everything. And this is saying to you guys, you don't get fully everything because you are measuring with the wrong tool. You're measuring with the wrong units. You're measuring with the wrong dimension. You're measuring the wrong dimensions, and you're measuring with the wrong tools, wrong dimensions. Example, you get the Boyle's law, you get the wrong factor, which is doing the measurement itself. This is actually measurement. So you get the measurement of the self, measurement of the system. So you get the measurement here. So example, this is like the light speed, but this is x to prime, but this is like the Gaussian transformation. I don't really know. What you say is like you're measuring instead of dimension behind, because you don't really if you're doing a static Lorentz transform, you have to evolve with the growth of the system. Based on its movement, based on resistance. So it's like a picking the system, dimension in. It's like teleport. If you don't enter the right, if you enter a dimension that's far, if you keep going faster, near light speed, you're entering dimensions. You can teleport. You can start teleporting because you can just that's why I see this is something. You can really just teleport the dimension because you are really in one dimension of light, and light can allow you to teleport. Because if you're going at light speed, there's no point of really just having that speed forever. You just have to start teleporting. You have to start using other properties of quantum physics. You're quantum lattice. You're in a quantum lattice, which is dimensionless, which is dimension, which you are getting dimensionless. You're not losing dimensions, you're getting more dimensions, but you're not actually measuring dimensions. That's why you're not actually like measuring dimensions using the refraction, and that's the problem. For example, this is like 1 over square root of r. If this is one dimension, you get a half or square root of r dimension via the volume of the constant slice speed. If you got the speed, this is what to say. One dimension is like this 1 unit over the third of the dimension. This is like the signal you're processing. The third. Now this third is 1. The third is -1. So square root of -1 is what? Square root of 1 is what? -1. Yes. -1. So you what is this? Sorry. Oh, I didn't know. Yes. So sorry. Sorry. 1 second. So you get the square root of 1 over -1. So just like square root of 1 over -1. Now so you get to come there. It's like the more dimensions you enter, you get the lepton, and get the nuance. Now the one that has the 100 is the TOA, the T for tango, A for alpha, U for umbrella. So that gets the 100. That gets everything of nothing. That measures nothing to your others. The TOA is like the measure of absolute nothing. It wants to be nothing, but it's not absolutely nothing. It's like if I'm going so far, do I prefer stability or just becoming nothing? Getting a mass, but if you measure a TOA, you are in a state of equilibrium. Basically, you're teleporting. You have just transcended. You're just basically you're moving to transmitting. If you're in light speed, you're teleporting. But if you're at 12 speed, you're getting so this 10 units, 10 times 10. 10 units, 10 kilograms, no, 50 kilos with it. If you're driving for 10, if you're flying from 10 feet, basically, if you're flying, let me just see where you're gonna be. 50 to the power of 100. Okay, let's say 50 times 10 times 10 times you get 210 feet. 10 to the power of 3. 10 to the power of 3 is what? 1,000. 10 to the power of 3 is 1,000. 1,000 kg. And that's really because you're on a third dimension of axis. Basically you're working on 3 axes. That's what the TOA is. Basically they work on meters. So basically, if you can move in this world physically, you're weighted by gravity, which is what the leptons. You're in Leptonian world. You're bound by Leptonian gravity, which I like to call it. And if you get the more M for Mike, U for umbrella. Over, so you're bound by what? The features of the space-time curvature over the being space. It's like being in space, but you are moving at the speed the speed any observer literally asks. That's what you gotta be. That's what. Sorry. So basically, I'm gonna go up now. Don't worry. That's the lowest factor. Literally, what you gotta do. So basically, the twa is the equilibrium. The mu1, basically is the dimension above, below it, and that's when the compression starts happening. Doesn't matter how far you go. You have to use a twa to go to teleport, to start teleport. You have to be between the more speed, so you can get the more speed by plugging this function in. So remember, is if you have a weight, if your ship has a weight of 1,000 kg, or let's say 500, 1,000 kg, which is the maximum, and you're good at light speed. What's light speed? The light speed is one. I'm gonna try to work this out. Light speed. Simply, you know what I'm saying. So you have to like distill the pressure. You distill. You don't distill. You have to switch the dimensions of your M to get the right tools. You know, if you're measuring the wrong system, if you're using the wrong system, basically it's a time series graph. If you're doing the wrong derivatives at the wrong time, if you basically when you switch the derivative, wait, how do I do this? How do I give me? Okay, let me just give me this formula. Give me a problem using two sets of potential differential equations for this given 1,000 kg and into 500 into potential differential equation for pressure and time using pressure and velocity in Lorentz. So let me just solve this problem. Let me see whether they can give me a problem I can solve. I don't think I'll solve this problem, but I'll see what I can do. You will not give me a problem. You will not give me a problem. I swear, I won't give you a problem. If it doesn't give me a problem, I don't really want to tackle it. But I know it's like a problem for me if I don't tackle it. Let me just try this way for it. Bernoulli principle. You're not asking a good question. I know it can give me a question, but I just want to ask you what can give me a question. Acute. So e to the power of I squared plus so equals plus 1. I guess I get plus 1. So problem statement. So let's try this from. If I first like obviously the mass is 1,000 kg. 1,000 kg. A cube. Let me try to get this properly. I know I'm doing. Let me see properly. I'm gonna go up now. This is going up properly. It's not really I have to see it properly because like I was gonna see my face. Like it's gonna annoy me. I'm gonna see my face. I don't need to see anything else but my face is from. Basically a problem. Obviously mass is 1,000 kg. 1,000 kg. It's a cube of silent L0 equals 1 meters. Rest frame. Just the rest frame is just the still state. It flows at a neutrality of a fluid psi. That's psi. P equals 12 kilometers per divided by meters cubed. Or rise density. Basically just the volume. That's basically this is what I'm saying. So basically, object of mass m is a cube. Cube is a dimension, has a dimension as a volume, so it's a volume. So immediately, I already know it's a derivative of the direction. So I just know that the derivative. You have to do it over time, but I know I can use the derivative of the two levels. So I have to divide two equations here. But I'm dividing. Sorry, I'm doing properly. I'm doing wrongly. So I'm going to. So the mass is 1,000 kg. So this is like a paper I don't really need. I keep like messing up. Alright, I'm really unhappy with that. Because you know this is what I'm saying. It annoys me literally. It annoys me because I'm not doing it the way I want to. So the mass of a cube equals 1,000. That's equals silence L. Mass of a cube is m. And then the silence is what? Silence is L0 equals 1 meter. 1 meter. So 1 meter does be L3. That's L3. That's L3 equals Ln equals is set of L to Ln equals n to the power of m. That will be cubed. As well, basically I'm saying rest frame of 1. It flows neutrally in the density phi. equals 12,000 kilometers rest city. So the rest city, where both rest the object set horizontal because the 0.8 is constant. Obviously, it's relative. 0.8 is just everything travel time. So this dimensions are by launch factor. Due to the dimensions along the direction of motion are reduced to launch factor. Perpendicular motion remains unchanged. That's a right angle motion. Perpendicular things are a right angle. But perpendicular, no. This is perpendicular, no. Right angle, no. Parallel, yes. Assume dimensions are incomparable to density and change 9.8 meters per second is gravity. The constant time is 3 and then times 10. Let's calculate 5 for every 0.8 second. Basically, you get to one of the number one is just the volume. So if you have the volume, that's just the volume or the maximum density the whole share. That'll be one. So this is you get two functions. One volume, that'll be one volume of dimension. So phi is 0.5 second, but that's what the last one for things is. So let's call the dimension. Dimension D. The level is one. The first one comes in one dimension, which is the one right dimension. Basically one right dimension is two left dimensions, one right. So this one left dimension. This will be sorry, this will be somewhere L. But this one left. This is one left. This is like a one left. But this half or this was or half or one left dimension. This left dimension is like a phi. But this phi is one. But this one is like a XYZ. So you get like dimensions are perpendicular to it, and now B. 5. So just you get dimension L0, L11, L to the power 3. So the summing dimension is 1 to the power 3. If you get dimensions left 3. So you have the left 3, L0. So you get L0, L3. L to the power 3 is dimensions for density left. That'll be 5, 0.8 seconds. But this is I don't really want to think about this. We can get the strange forward. You get one level, but this is time. So the pressure of this is 1. Basically, I'm trying to give you the kind of transformation you need. So this one, guidance solution, this is like a guidance solution. So you can't solve them. You'd like to solve it for me. Basically, it solved it for me. I'm not really happy you solved it for me. I don't really wanna. This is L to 0, this is L0 to 3, 1 to 3 squared. This is like it solved it for me. I hate the solution really. It's just like the fluid rest space is like the buoyancy effect. It's like the buoyant force of the force 0 B is P compute FB in moving cube is moving cube. So basically, the buoyancy force is the dimension force, the kind of thing that in one dimension. But you know, the TWA is one the maximum dimension can go to, and that's what the TWA is. It's like measure of nothing. But that nothing is the entire dimension of measurement. It's like you get 1,000 and you get 1. You get 1. And the difference of between 1,000 divided by 1, 10. You get basically you share a shade of 10%, 10% of growth factor. So you get 10%, 10% is the growth factor. So you get 1,000 kilograms divided by what? 1 times which is one dimension of space and time, and 1,000 the kilograms per second per no psi. Let's try and calculate that. 1,000 psi for every 30 seconds. Because you know you don't have to every half second completely, every half. So you have to half everything in space and time. So every half second completely. Let me try to do a calculation question here. Get 1,000 psi. Let me try to think about this problem. So basically 1,000 psi. This will be 1,000 psi calculator. So basically you have to state for half of everything. So basically you get a value. So everything, so when we say that everything 1,000 kg share half in density, and that density is the volume. So you have a half of the volume. So everything is just be halved to get a chemical state. So you have to half everything. 1,000 divided by 2 is 500 kilograms. But 500 kilograms is just if you have 500 kilograms, you get 1,000 divided by 2 is 500 kilograms. But you have to share 250. So you get 2 halves of 1,000 kg divided by 2 is what? Obviously, this is a rubbish PSI calculator. I really had one open, I just lost it. I just didn't know I kept it literally. Basically, it's like a 1,000. It's like a boat derivative. This like bore's diameter is what? 5. So get 1,000, 10. So get diameter is just 10, but you get 5, but you get the diameter, but you get you use it in pi, so you get pi r squared. This is pi r squared, but you get pi squared 2 pi r. 2 pi r. So the share half of it is, so you get to half the time, the speed. So you have 10,000 kilograms mass, so you get what? 5,000. 5,000. No, 1,000 divided by 10. They share 10% of everything because they evolve together. That will 1,000 by 10 is 100. 100 plus 100 kg of space and time is the pressure. And that will be piston pressure. 1,000 kg. This is modulo kg. Kilonewtons are basically this is the piston force in newtons, but I don't see the kg. Basically, what I need kilonewtons are basically 10 kilonewtons. 100 kilonewtons is what? 100 kilonewtons is like 1,000 kilonewtons is like 5, and that would be psi. 100 kilonewtons bare meters. So piston 1,000 if the piston force is 1,000, and the diameter is 10, that means there's a trade-off, and basically you get the bore area of bore area is like the full area. So make it the I'm just writing it down properly now. So you go to calculate the thing. So everything if the 100 is in the state of state, you get 1,000 divided by 10, which is the bore diameter, which is 5.5. Because the diameter is 10, you need to be 1 to 10. But you get 10% of a steady state, which one makes sure that 10 is shared. And that'll be one shared state that's 10% you can share because it's stable. It's stable, it's not 5%, literally. But 10% of this kind of pressure is what? The bar, cylinder pressure. But cylinder pressure is like the pounds per square inch. This one is like pounds per square inch of psi is psi of cylinder pressure, which is like the pressure in a cylinder, from a cylinder, on a cylinder, because it's pressure onto a system. It's 1,060, but this is pressure where you don't want to put your hand like under the cylinder. So basically, on the cylinder, what's going to compress, and the bore area is like 8.54, and the bore diameter is 10. So basically, that's what's stable. And we get this kind of physics, we get some kind of calculator. So it's like the pressure one, but we don't calculate that. We only calculate the kind of space, the kind of temperature, but it's temperature calculate like a pressure. Temperature. So let me see. Try to get temperature. Oh no. So get the temperature. Temperature at sea level. Basically, you get this kind of. So you get the same thing. In artificial, you get basically you get this on axis. What does that mean? So the 10 units are in axis. So the 10 plus 10 is to get basically get so this 10% is wrong. It's not really right. So this is a dimension of time. So this is 10,000 psi, but this is just one axis of dimension. So you have to get the thing cut off at some kind of more units. So if you take the derivative of this kind of system, the pi 360 is one of polar rotation left. But you need two polars, which is like a 360 by 360, which is 720. So this is two. I think what I mean by two axes. You have to get the constant time of two axes. That means you have to get the third derivative of the left axis. Basically, you have to get two left rotation. That'll be 362 times 2, which will be 360 times 2 is what? 360 times 2. Which will be 720. So you have to rotate 20 seconds to get one right polar axis. Basically, if you're going at the speed and you exceed something that has a pressure, that's the speed, the speed or the pressure in any dimension you're in, and if you use polar coordinate system, that is no contagion. On the lattice, you get 720, and that's two full left rotation. Basically, you have to now start measuring the opposite of the large system because you can't get any information from the you have to use the same Lorentz factor, which I'm going to do to get the same transformation. Because if you have f prime, you have to find the derivative of prime, the third derivative which is prime, which is called a jerk. Now the jerk is like a jerk of which is a constant jerk. So it can be 18 milliseconds. For example, let's say it's 18 milliseconds. Let's just say it's 18 milliseconds. Let's go because I don't really want to do this kind of thing. So you have the pressure and the time. Still to some kind of solution. Oh, I got something here. Can I No, normally you got this now. Let me just stop this now. Let me just try auto save. Let me start again because I'm gonna do one more thing.